Hello everyone and welcome to Handmade Hero Show. We code a complete game live on stream. We stopped yesterday just at the point where we need to do debugging of our import code, and we also need one other thing, which is we wanted to have a way of taking checksums of our input files, so we would have a little bit more than just the date to go on. Now here's the problem. I don't have a strong opinion on what we should implement for a checksum. Anything will do, but some things are significantly better than others, right? Like, you know. The better the hash we use, the more resilient it is to collisions, the less likely it is to do something spurious. And who knows what that would actually end up looking like in practice. Certainly it's not that hard. If something is refusing to import because it thinks it's already changed, we can always just have a button that's like, force it to import this file, and it'll re-import the file. So the, the cost of a hash collision in our world is pretty low, and so it's not really very important for us to get this right. There are cases where it's way more important to get it right, and it costs a lot if you get it wrong. Code signing and those sorts of things would be places where you really don't want to have collisions be easy to generate because attackers can spoof things. We don't have attackers in this case. Anyone can import a file if they want to, and this hash is not being used to prevent anything. It's actually just being used as a minor speed up to prevent files from being reloaded if they don't have to. So it's a very low risk endeavor for us, and any hash will really do. The question is, which hash should we do? And I don't know, so let's take a spin around the internet and see. If I say, let's get a fast, good file hash, what will it say? Has anyone done a good analysis? Extremely fast non-cryptographic hash. Well, that sounds pretty good, but how is it in terms of resiliency? You know, I don't know. Let's see. Let's see here. Well, it's got a quality metric, right? Who knows? That seems nice. It's fast, right? Let's take a look at what the code looks like. Here's a C++ version. Is there just a document that says what the algorithm is, by the way? So it looks like it's one that uses some tables, which isn't necessarily a bad thing. A lot of CRCs use tables. Like, for example, the original CRC32 stuff, they use tables. Not sure if they have them in here somewhere. A lot of the original CRC stuff use tables. And it looks like they do a lot of rotations and rounding here. What? This must be round, like a cryptographic round, not actually rounding, right? What is this round? Like, they're not in float, right? So round n must be their round, like their cryptographic round. Well, I don't know where that actually is defined. Here it is. Yeah. So it's basically just a rotation, and then it picks the prime. So it is a cryptographic round. It does a particular rotation and then does a picks out one of the primes that it wants. Is there just a description of the algorithm somewhere? Do we get that, or is that not on the table for some reason? don't know why there isn't just a thing that's... here we go. Well, no. Thought I was going to find an article. Let's take out murmur as well, because murmur I've used before and I like better. It's pretty simple. It's a pretty basic hash, right? Very, very simple. Doesn't use a table. And looks like the quality, at least by whatever these benchmarks, however it's measuring it, which I don't really know how they're actually measuring these in terms of hash qualities. It looks like the quality would be similar. We don't care too much about the peak speed there. And just the simplicity would be nice. Now, like I said, XXHash might have a simpler version. It would be, I wish they had a simple thing here that explained the algorithm, right? Because here's here's the example. It's like, here's a very simple explanation of the algorithm. So, you know, I don't necessarily want something when I'm just initially looking and trying to understand what something's doing. I don't want to look at highly optimized code that who knows what it's got in there, and that, you know what I mean? Like, I don't want to look at all that stuff. I just want a simple explanation, what's it doing, so I can see, you know, basically what's going on. You can see here that it's basically got like a while loop that does 32 bits at a time. And, you know, we could just make it so that it's always 32 bits at a time if we wanted to. We could just enforce that. So we could literally make the murmur hash be like that big, and then it just does that final bit there, right? So this is a really straightforward hash, which I think makes it maybe a better choice, because I don't want something complicated. I just want something reasonable. It would be nice if we had a 64-bit murmur hash, because we can store 64 bits and work with 64 bits on a 64-bit machine really easily. And so I kind of would have preferred that. Let me see if there's a 64-bit murmur hash. Yeah. So this one wasn't 64, right? Yeah, so this was the 32 only. So basically, this hash here is a 64-bit version of murmur. That seems maybe like a little bit better. Go in here. So here you can see, again, very, very simple, right? I like the looks of this one a lot better. They've got a lot of stuff in here, right? You can see them, again, much like the XXHash stuff. One of the problems with these is they always like expand them out because they're trying to be performant, you know? And so if I just want to look at something simple, sometimes you end up in a bad situation where you've got to wade through a bunch of that code I don't really care about. But it's, you know, it's to be expected. Either way, that seems pretty good to me. Let me go forward there. I didn't know it was no space in between those two. So I feel like that's pretty reasonable. Murmur hash 3 might be what we want to do. And here's the, like, you know, the thing that I wanted, which was the description. So basically, it says, here's a thing, like a mixer. It's pretty basic, right? I multiply by a constant. I rotate. I multiply by another constant. I take the XOR, right? So this thing that I've prepared here, which is K, this is not the same as H. So I've got two values I'm tracking. So I update my K with a multiply, a rotation, a multiply. I XOR my hash value. I assume the H is the hash value. I don't really know yet. I XOR my H value with my K, which is the thing that I was updating. I rotate that, and then I do a multiply and an add here with constants, right? And so it looks like K is what I'm reading in. H is the hash value, right? pretty, if that's really how simple it is, right? I just like how basic that is. And then the finalizer, this is if I want a 32-bit value, this is if I want a 64-bit value, right? I don't know what these values are supposed to be. I don't know if these are supposed to be 64-bit or not. Let me see here. Yeah, so those are so this is assuming these are 64-bit. So here's the 64-bit finalizer, because you couldn't shift something down 33 bits if it wasn't, right? It would just be 0. So these are 64-bit values, or at least H is. I don't know if K is expected to also be 64 bits or not. So I think that's pretty easy for us to do. And I'm just going to go ahead and do it. Yeah, that seems good. And we could, if we want to make it easier on ourselves, again, just like pad it out. But I guess even that's something we'd probably be pretty trivial for us to handle this, the end of it. Pretty straightforward to handle the end of it special as well. So let's just take a look. And again, the reason that I'm just going by stuff on the web for this is that I just don't have any cryptographic skills whatsoever. So I don't really have the ability to evaluate cryptographic things. I can't like look at two hash functions and tell you which one I think will be more collision resistant. I just can't. So I have to go by other people's public testing and attestation. That's the best I can do. If I was doing something that was really cryptographically important, which is not something I ever do, I would probably have to take the time to learn a lot more numerical analysis so that I could start to have an opinion about things like that. I just don't have that knowledge at all. So I have to trust other experts who say that things are stronger or weaker, and off you go. Murmur hash is supposed to be a fast hash that's just reasonable for files. It is not a particularly strong hash by comparison to like a real cryptographic hash, like or one that's intended for cryptographic use, like Keccak Sponge, or the or even like a SHA the SHA one before it, SHA 2 or whatever. I don't think the Murmur hash is meant to compete with those. It's supposed to be more of a high-speed hash for doing things like this, just checking files, where you assume that there's no attacker who's trying to thwart you. So I'm pretty sure a Murmur hash is not something you would ever use in a cryptographic setting. A cryptography person is welcome to correct me if there are any watching, but I'm pretty sure that that's it's not that kind of hash. But it's a fine hash for file things, to the best of my knowledge, and we don't want to waste a lot of time doing hashing, so that's why I wanted to go with this. So if I go into the shared code here, so this is Murmur hash 3 in particular that we're doing. And I say based on here because, you know, I'm not really going to test it thoroughly or make sure that I even comply with what they were doing. And so I don't want to say this is a Murmur hash because it might not quite be a Murmur hash. It might be our own secret non-thing that isn't really a Murmur hash. All right. So what I want to do here is I want to make a hash update like we had before. And that's just a little function that's going to do this, right? So it's going to be a K and an H, right? And it's going to return the H value to us because K doesn't get stored. K is read in. So what I want to do here is I want to say, okay, K times equals C1. We got to know what, oop, that's not good. We're going to have to find out what that constant is, but that's fine. Then we want to do rotate left. And we have, if I remember correctly, a rotate left here, right? The problem is we don't have a rotate left for 64-bit. And so we're going to have to look. I don't actually know if there is one. I assume Intel put one in. But even if they didn't, you can see here how we implemented the rotate left in terms of regular operations, right? Ones that didn't require a ROT-L. So I can do one of these rotate lefts with 64-bit if I wanted to by just doing that, right? So here where we do the knockout of the value, we would just have to do like, oh, okay, you know, it's not and 31 anymore because this is 31 was there because it's 32 minus 1, right? So we would want to do and 63 here, right, to make sure that we are clipping off whatever the sign is, if there is a sign. So what we want to do here is make sure that we can do a 64-bit one. I don't actually know if we can. There may be a ROT-L64 of some kind. I'm not sure. So we'll have to check that out. If there isn't, then what we can do is, again, just do probably the same thing here, and it should just work, right? Because all we're doing is doing 2 shifts to put the things in the right position, then OR them together. That's all that the rotation would be doing anyway, so it should be fine. Now, I think we should be able to use our search, hopefully to find some of these things if they exist, so that we can just call the compiler intrinsic if there is one. Let's find out. I don't remember if there is or isn't. So we know, we know there should be an underscore ROT-L. So let's go ahead and try to get that. Yeah, so you can see it here. So let's try and find, like, is there a ROT-L64? Yep. So you can see here there's a ROT-L64, so that means that I think, in theory anyway, we should be able to just stick a 64 on here and have it. I don't actually know if that's true, but hopefully it is. So it looks like it's S64 is what it's actually, I'm sorry, int is what it's actually wanting for the amount. And now I think about it, that's, you know what, that's actually, we don't need a 64-bit shift value, right? You can only shift by up to 64 bits anyway. So this could be an 8-bit integer for all we care about, right? It's just not relevant. So I don't know why I did that. I was just kind of not thinking particularly hard about it. Okay, so if we want to do a rotate left as we were instructed to do, we can do that in 64 bits. It's no big deal. So we want to rotate by that R1 constant, which, again, we're going to have to find out what they actually want because these constants are important. So we've got a C1, an R1, and a C2. That's going to affect our K. Then we want to do the XOR here with whatever we mixed up. We are now going to do the XOR. That's the end of our use of K. Now we're going to do further operations on the hash value itself. So this is like the hash update step. Again, we're rotating left. We're rotating the hash left. And we're using the same constant for the rotation as we did with our K. We then do a multiply step. So there's an M1 plus an N1 there. And then finally, we return the new H value. And so this is sort of, and in fact, I probably should put this here because it's really, this is the part that we're using. This part is just going to read this. This part has nothing to do with the mirror hash. This is just the part that's going to iterate over the buffer calling hash update, right? So then we have the finalization step. And the finalization step is going to be the 64-bit one here. Now, I don't know why they chose to include the constants here and not here. I'm not quite sure about that, and so we'll have to read a little bit further on and find out what... I don't really know what that... Yeah. I don't know why they chose to have some of the constants and not others. So, you know, it's probably because they just wanted to write this once and they didn't want to write it each time for 32-bit, 64-bit, whatever bit, right? That's probably why, because they're going to use different constants for the two. So this probably just wanted to condense, I'm guessing. But either way, this is what we want to do here. It's basically just like two constants and a bunch of XOR shifts, which is fine. So murmur hash, murmur hash finalize. So this is just going to take the hash value. It doesn't use any new information. In fact, I might put the H at the front. So it's basically like you always pass the hash value, and the K is like the new thing that you're feeding in, right? So now if I want to generate the finalization, I just have to do this is an XOR shift, and I'm doing the same XOR shift like 3 times. Right, so we shift down through 3. I don't remember if this has to be U64, but I'm going to make sure it is, just to make sure there's no weirdness there. And then in between each of these, we need to multiply by the constants. So I'm going to put those in here. And again, those also, I think, have to be potentially... I don't know how smart the compiler is in terms of understanding that these are supposed to be 64 bits. You could also do that, I believe. I think. Not really sure. But I believe that tells it, hey, look, make it a 64-bit unsigned, please. And you can just stick that on the end of anything when you actually care there. So I just wanted to make sure that was operating in 64-bit, and then we return it. So that gives us what we need to do our murmur hash. What I don't know is where to get these constants from, because now we have to know what they are specific to the particular routine. And so to find that, I'm going to just go look at the actual code, because obviously if they oops, that's the issues. If they implemented it, then they're going to have to put the constants in somewhere. So let's take a look. So here's the murmur hash stuff. I assume I can just go in here to murmur hash 3.h, look and see what we've got. So we are trying to do a 64-bit one. I don't see the 64-bit one, though, which isn't great. Okay. So it looks like they have their RODL 64, right, doing the same thing we were doing. So this looks like the part that we just implemented. So there's their finalizer for 64-bit. We did not do the 32-bit finalizer because we don't care about it. Here's their 32-bit operation. And you can see they've defined the constants for the 32-bit version. So the thing that makes me nervous here is it looks like they don't really have a 64-bit only version. It looks like they only do 128s here, right? I don't know what to make of that. I'm not sure why they did that, because if you look, they actually do 2 64-bit mixing steps at the end. So they're actually mixing these together here. I'm not sure what the deal is with that. Why they do 2 128s. That's really strange. So you can see the way they're doing it. You've got, what they're doing is they're doing 128 bits at a time by maintaining 2 64-bit hash values, right? Now, I'm assuming because these are 64-bit, if we want to, we can just use the constants that for the 64-bit version, because they're telling us what they are, right? So rather than doing 2 and mixing them together, I think we can just extract the constants we want out and do it the way we're doing it. I don't see a lot of reason not to. Here's the C1 value, right? So that's C1. Here's the C2 value. So those are the 2 pieces we need here. And, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 1 correct this comment a little bit. So we're not going to do two at once and mix them because I don't even know why that's the only other thing they did. They must have a good reason. I mean, they wrote the hash in the first place. They obviously know what they're doing. But they just don't want to do that. So we can see what we want to see here. Here's the step, right? And what's particularly odd about this step, and I do not know why they're doing this, is that they're different, right? So they're generating a hash value for K2 that's different than the way or for H2 that's different from H1, right? It uses 27 or 31. It uses two different constants here. And so I don't know why they're doing that for subsequent blocks. It must have to do with the fact that they're going to mix the blocks values together later using this, I guess. No, that's just for the tail. I don't know why. So this, right? The H1 plus H2, they must be doing this because they're doing this part. They're like cross-mixing the hash values, right? So I really just don't quite get that, which makes me a little nervous. I wish I knew why they were doing that. If we take a look at the original Murmur hash, so here's the basic one, right? It's 15, 13, and 5 for those. And then it's, E654, B64, or whatever, right? So these are completely different, except for the 5. The 5 remains. So these shifts are up more, which would make sense because they're 64-bit. These are presumably picked because they're being mixed together. What I don't know is if we just want to maintain one hash value, which of these would be better, or should there be some third as yet unnamed constants that we should be using? Okay, so in Murmur hash 2, they do have a 64-bit version. So what goes on here? So this is a simpler hash, actually. And I guess they decided to change it? Because this is totally different. I mean, not totally different, but it's quite a bit different. So I'm not sure what to make of that. I don't quite understand why they wouldn't have provided a 64-bit version, and I wish there was some explanation in here, but I see nothing that even mentions that fact. And that's a little troubling. I like superfast hash.cpp. So I don't know. What do you think we should do? Maybe we should just ask. Dear sirs, which constants would you use if you were only going to produce a single 64-bit hash value and not try to hash 128 bits at once? You know? And I don't know. So I'm going to just go with this mixing step. Like I said, we don't have a lot of risk here. So I'm going to go with this mixing step. We have our C1. We have our C2. We just need to know what our rotate left's going to be. So we'll just say it's 31, right? And then here we've got our other rotate is 27. So then we just need our M1, which we know is 5, and our N1, which, again, this is the part that we really just don't know. But our N1 is going to be the first constant because I'm just purely ignorantly picking the first mix because I can, right? That's it. Now, as with any of these things, and this is the downside of not knowing any numerical analysis, I have no idea how good this is, right? Like, I have literally no idea. I know what it's doing, right? I can see how it works. It's pretty straightforward, the math that's going on, but what that math actually accomplishes is totally opaque to me, right? Like, I wouldn't know if you were to change this 2 to a 3, what would be, like, does it matter, right? I have no idea. These constants were chosen probably very specifically to do certain operations to the bits and put them in special positions and make them be dependent on each other in a special way. I have no idea how it's working, right? And so it's a little bit frustrating. Again, the reason I don't know these things is because it never actually matters to code that I write. It's usually sufficient to take someone who has made a good hash that's relatively well respected to just take their word for it. It's usually good enough because, again, if you just pick something relatively simple like this, you know, you can usually put it in a relatively small amount of space. You don't have to think about it too much. And if the cost of it being bad isn't that high, well, it's okay, right? But again, it's a little bit nerve-wracking because you can see how if, let's suppose, we actually really cared how good this was, we would have to go spend a ton of time trying to figure out exactly how this thing was working before we could have any confidence that it works well at all. And of course, the supremely unsatisfying part about all of it, as with anything in cryptography, we don't really know. Like, even the best cryptographers really don't know how hard something is to crack, right? All we really know is that no one's cracked it yet, right? Or things like that. And so we don't have ways of proving things are unbreakable. We don't have ways of proving things can't have collisions generated for them. We haven't gotten there yet. I mean, that's like cutting edge stuff, right? And so, you know, it's kind of a supremely unsatisfying thing in its entirety because a lot of times even the best people can't really tell you. They might be able to tell you, well, this one's weaker than this one because we found this many exploits to it, or we can go through these parts of it more easily and stuff like that. But it's right, we don't really know much more than that. And we can also evaluate them in practice. If we just take a bunch of random stuff and feed it through it, how often is it colliding with small permutations in the data or stuff like that, right? We can do some testing and that's, you know, maybe that's as good as it gets, right? So again, it's not a very satisfying thing, but luckily for us, like I was saying, we don't have to care. We're in the enviable position of really it doesn't matter, and that's really nice for us because it means we can't fail too hard, and that's really what you want when you're going into something cryptographic, because if failure is on the table, ooh, it's rough, it's nerve-wracking. Okay, so let's start here by creating our result. I want to note here that the seed values are often passed in. That's if we wanted to get some additional information in here from outside. We still can do that. I don't know that we really care, but if we wanted to, we could do that just by saying something like this, right? Where we say, look, if you want to pass in a seed value, go right ahead. That will be the initial state of the hash, and then when we go through and do the hashing, we'll start from there and update as we go. Now, we know we're going to have a hash value. That is that result. I guess I don't need to do it that way. So what we're pretty much going to look at is something that does the hash finalize at the end by taking what we get as our last hash value and passing it through the finalization step. That finalization step, again, shifting out the low bits here in a sense. So shifting it over and then XORing. So it's kind of mixing, it's mixing in itself through 2 rounds of multiplies. I don't know why, right? I don't know what's magic about those constants. That's, again, the thing that we, maybe if there's a paper on murmur hash, we could go read and find out why. But basically that step, we're taking the value, we're shifting it over, XORing it in on the bottom, shifting it over, XORing it on the bottom, shifting it over, XORing it in on the bottom. So we're really mixing up those bottom bits that way, and I'm not quite sure why. I don't know if that has something to do with the fact that we're less sure about our bottom bits or something. You got me. That's for the numerical analysts to worry about. So anyway, when we go to do our checksum here, what we want to do is we want to read out 64-bit values. So what I want to do first is I just want to find out the count here. So I want to say, look, how many 64-bit values could I do? So we know the buffer has a count, and we know that if we divided that by 8, or maybe if I'm feeling saucier, I could just say size of U64. So however many of these we're actually going to do, that's our count 64. And then we've got like a count that's going to be a byte count. So how many 8s do we have, right? And that's going to be however many there are in the buffer minus the count 64 times the size of a U64. So what I'm doing there is saying, look, how many packets of 64 bits can I process, right? And then how many 8s are left over once I'm done? So that means I can go fast, right? I can just say, all right, let's loop through all of those. I'm just going to loop through all of the 64-bit ones that I have here. And what I'm going to do is I'm going to snap a 64-bit pointer to the data. And it's just worth noting here, and maybe I should make this a to-do. So on Intel machines, they don't care very much about alignment anymore. They really just don't. I guess they found that having the lanes move around was not as big of a deal as it could be. I really don't know why it used to be a problem for them and now doesn't seem to be. But operating on 64s that are offset, it doesn't tend to be a huge problem anymore. It used to be a much bigger problem. So at the moment, I'm not going to care about that. But if in the future we do care about that, what we would want to do there is step to the first aligned 64-bit boundary and then just go 64 bits along, right? So you can see why that might be important depending on the platform. So we'd have to see. Since this is only used in imports, we probably will never care about it, but again, it's just worth putting it to do there because we know it could be a problem. Might as well put it to do so that when people are searching the code base, they can see, and maybe it heads off some problems for them. Who knows, right? I guess I can do this. Every time I read one of these things, I want to update the murmur hash, right? So my result is going to be a murmur hash update step. Where I pass in the current result, and I read in the next 64-bit value from the data. That gives me a new update. When I'm at the very end here, I need to load in one final 64-bit value to suck up any of the additional 8 parts that I've got. So what I'm going to do here is make a residual. I'm going to snap a pointer to the residual, and I'm just going to fill it, right, with whatever's left. So here's the count 8. That's how many bytes are left over. And I'm just going to say, look, copy from at, wherever we ended, copy the remaining bytes, put them into my 64-bit value that I've got here. and it'll just fill them in. Now, technically, right, you might have to think about which direction you wanted to go. Do you want to fill the top bits in, or do you want to fill the bottom bits in? Because since it's little endian, you know, if you look at what happens when you grab a 64-bit value, the first thing goes into the bottom that goes up. It just so happens that doing this copy would fill in the same order that that grab would fill. So the missing parts are coming in the right place, right? The zeros will be in the right place. On a big endian machine, this would be wrong. It would be the wrong way around. Since we don't actually care, however, meaning it's just however we want to do the residual is how we do it. As long as we do the hash consistently both times, it's okay. It should be fine. But it's worth noting that if we were to run that checksum on a little endian machine and a big endian machine, this would produce potentially different results, right? So basically, we don't want to support big endian machines because I hate the fact that endianness is still a thing, and we have all little endian machines in consumer space right now, and we should stay that way. So I'm just going to leave it like this, and everyone has a big endian machine can eat on it. So what we want to do here is finish off that residual by doing one final murmur hash step where we can pass in, again, the same format that we had before, but now we're just going to do that residual. This step obviously only needs to be done if there was a residual, so we can just check the count 8 first and just skip all this nonsense. In the case where there wasn't any residual, this will automatically skip itself because this first check will fail, so we don't really need to do anything about that. That should be the entirety of the hash. That should give us back the hash code that we wanted. So now when we import things, we should get that checksum. This also means that in the HHA edit, in theory, when we produce that checksum value, the source file checksum stuff here, we could actually produce the synthetic checksum for the file if we really wanted to. I don't know that we really do want to, but when we do the read HHA v0 and we produce that synthetic annotation, this part here, we could actually produce the file date and checksum of the v0 that we read. I don't think it's worth it because I don't think we don't really support updating from a v0 to v1 file in a on-demand way, so it just doesn't seem like it would make any difference. So I think we just can leave it the way it is now, but it's nice to have that in here either way. So I think that's it. I think that's everything that we needed there. And so now we should be able to store that annotation data into the file. It should have the checksums for the files properly, and that should be, you know, I think what we want. So if we go in and start the debugging process now, we should be able to sort of go down the home stretch here of the art importing process. So here's the game running as it normally would, right? With the hero in, loading the sprites in. And what I remember us doing is when we made his fist be something that only comes from imported art assets, right? And so the question is, can we now go ahead and make the imported art assets work again and see if we can start testing that system? So if you remember correctly, the way we did that is we said we don't import by default. You have to create an HHA that's suitable for importing, and if it sees that there, it will start to use it to import art assets from the art directory, so from this directory. So if I wanted to do that, what I can do is I can run our HHA edit routine. As you can see, there's a -create on that. That -create is the thing that tells us, okay, let's make a new file here that we can use. And so we can make that local HHA. And that local HHA is what's going to trigger all of the dynamic loading stuff. So if we create one of those, we can also take a look at it, right? Here's the dump. It starts out with no assets, no tags, no annotations, nothing, right? It's a version 1 file, and that's all that's in there, is literally nothing. So if I now run the game, we should be able to step through our new code, and it should actually run and do stuff. And that's what we want to see here. I don't want this nonsense, so I'm going to get rid of it. So what I want to do is I want to step into here. I want to see us get this path. I want to see this path get hit, right? And so the file high watermark is 128. The idea is that should be the header, right? And you can see that it is, because there's nothing in the file. So the first place we would write is right after the header, because nothing in here, right? Allow editing becomes true, which is good. And it's our new default append. So HHA5 is what we're going to append through to. When we see an asset, we don't know where it goes. It's going to go in here. Okay. So then we come through and we allocate our arrays. We're using our large arrays, so we've got tons of extra space in there to put new assets in if we want to load them. That's exactly what we want. I should probably put an if here on whether there's anything to append to, because, I mean, we don't need to do it, but, you know, technically, even if it's Handmade internal, we don't need space if we're not running in append mode. But, you know, whatever. So if we come through here now, what I'm most interested in is just this path here. This is the path that has not been run yet. It's not going to do anything at the moment. Unfortunately, for you know what? I forgot to set another breakpoint. That was bad. Well, we hit an assertion anyway, so that's fine. What I was going to say is I wanted to step to that code, but then I realized as soon as I hit F5, I was like, wait a minute, it's not going to run, because that part of the code here would only run if there were any assets in the file. This is the thing that like brings in asset information from the existing file for importing purposes. Obviously, that's not going to fly because, well, I mean, for obvious reasons, there is no, there are no assets in this local file. So there's no information to pull in this case. So all right, so I can't debug that path yet. I've got to wait till the next time we load, but I can debug the rest of the path. So let's go ahead and do that. Now, we've got an assertion here, so we can start with this, although I would have liked to have stepped through this stuff first, but that's okay. We look here and we see we're supposed to have 13 tags. We wrote 208 tags. Is that right? So that seems bad, to say the least. So I'm not sure exactly how that ended up happening. We were supposed to write 13 tags, and we wrote like an infinity of tags. So is that really what happened there? What did we do? So when we went to write... So I would like to step through that a little bit more carefully, and I think I can pretty easily. So if we look at what's going on here, if I just delete that local.hha and make a new one, I should just be able to step through that directly, which is what I want to do. I just want to watch this thing go. So let's just start there. All right, so first thing we want to know is how many assets do we have, and we want to count our tags. So let's take a look. If here's our asset that we're looping over, I'm going to set a breakpoint here as well. if this is our asset that we're looping over, you can see inside the HHA data, it's got the tag information here. It is one tag per. In fact, all of these are one tag per, right? So the tag count is looking pretty accurate there. So we get 13 tags and 13 assets. This could actually be set to a 1 here. I won't actually do that. Well, I'll do that later because I don't want to stop the debugging. So through here, I'm going to make 13 of everything. 13 tags, 13 assets, 13 annotations. Not a lot going on there. Pretty basic, right? So then we create arrays for each of these things. We're going to start by writing to the first one. Here's the source asset. If it doesn't match the file index, we don't write it. So we're going to want to stop when we get to, this is the same loop here. We're going to want to stop when we get to one that actually is in the file. So if I now look and check out the source asset, it's got one tag, right? So when I come through here, oh, that's the problem. This is not the right loop. It should be source, right? That's just wrong. So again, I wanted to fix this here. These nulls are skipped. Sorry, null asset. These are skipped. This is otherwise correct. This is the problem. This really wants to use this loop. Those are the tags we're trying to copy out. So we do. And then, when we're done here, we should now be able to wrap that up properly. So let's go ahead and run that. Should jump down there now after importing all the PNGs. Let's take a look. 13, 13, 13, 13. Much better. Now we can write out those pieces of information, and then we end. So that's all good. And you can see we actually do have the art asset there that we were interested in. So now I'm going to close that, and now I'm going to bring up tab view again. So I'm going to go into the bonus pack here. I'm going to use tab view, and I'm going to say, all right, let's dump local HHA to local.dump. Oh, right, and I'll never, you know what? We should just go fix that. I type it every single time, you'd think. So here's our imported file. What you can see here, hopefully, just want to underscore this. So this is why I spent the time on that HHA edit utility. This is just a really nice way for us to see what's going on, right? It gives us this nice debugging visualization. Right off the bat, I can see that this is set to unknown. Should it be? I don't think so. So we want to go fix that. That's something to do. I can sort of see that at least the checksums and the dates are set to something, right? I can look at the size of the data and see if it makes sense. It gives me a way of really testing things a little more deeply than I ever could stepping through and looking, because it's just, hey, now we kind of have a little bit more of a handle on it. Now this type unknown is bad news. We need to set that to bitmap, so we're not done yet. We want to do a little better here with that. So let's try one more time at initializing our system here. I'm going to do an HHA edit create local.hha. And then what I'd like to do is I'd like to just go into the code and find out where we were supposed to be setting that. So that information, if we go to the HHA file format, that information was supposed to tell us this, bitmap, sound, or font, right? It's supposed to give us a clear understanding of what this thing was. It's this thing here, right? And so no one's setting that right now. That's not getting labeled. So what I need to do is I need to make sure that it is. So when we find that we don't have an HHA, or I guess even when we do, we have to make sure we overwrite it. In all cases, I think. So when we come through here, we need to set that value. So when we're creating this part, in addition to the tag value, so we need the size, the offset, and you know, this could use the size too, even if it was less. So I think we want to do this here. We want to set that data size down to the asset data size in all cases. We want to just say, look, if the data size is greater than the asset data size, or sorry, if it's less than the asset data size, then we need to reserve a new one. But then we always truncate to that size, right? So I think that's actually more what we want there. This one, we need to always set the type. And again, that type is just, all it's saying is that it was a bitmap, because we wanted to make that a little bit more explicit. So it's like, it's a bitmap, keep that in mind, right? So let's try one more time with that fixed, and let's see if we can get this thing to look appropriate. I'm gonna go ahead and run here. This is doing the import. And remember, it's an unoptimized build. It's gonna be a kind of slow import as well. So that should have done the import. And now I should be able to dump that out and see what it shows up as. So if I now open one of these up, we can now see that the bitmap is actually correctly reported. It's got the correct size. That is how big the tiles were. And so this looks pretty good. I mean, that's good stuff, right? So I'm pretty pleased with that. So now we can check the next part of the process. The next part of the process is, can we rerun the game? And furthermore, if we make it through the reload stage, will our check for changes correctly identify that we do not need to import these files? Oh, and this part again too. This is good. We wanted to know this part. So let's see if we get the right source file name. Hand skeleton, that is the correct source file name. We got the sprite sheets going on there. We're gonna create the asset index. We're gonna write in this index, say that's what's currently sitting in that slot. Oh, I meant to look at that. My bad. Okay, so yeah. I think we have now correctly, we do not re-import. Well, title screen. Oh, yeah. Well, okay, right. So I guess I just check that. Yeah. So we do not re-import. So, and everything seems pretty good. The only problems we have now are I'm not seeing the actual asset, so I'm not sure we're actually labeling it properly. So we'll see about that in a second here. And in fact, we kind of know we're definitely not, because there's no tag. These are not tagged as a hand yet, right? So we've got to do that as well. All right, so we're getting there. Let's go ahead and finish up. if I remember correctly, we had sort of this thing where we searched for the basic category, right? And so we need to set that basic category. Where's those tag sets? Kind of did sort of a hacked thing here for temporary testing, and we might as well do that. So here's, yeah, you can see the tag stuff here. So if we wanted to make the basic category for these things be hand, we would just push 2 of them on there. So we would do like a reserve tags 2, and we would do like this. I don't remember what this was exactly, but it's like that, I think. So if we wanted to assign as a hand, we could do that. We look like this. When we actually go to make the tag buffers here, the difference would be that this is a +2, so each one gets 2 tags now. And now if we reran that import, that's what we would get, right? So let's do it. And I should be able to now go look at, well, and there's the whatever, the little test bitmap there. And now let's see what happens if I run it a second time. It's still there. So I think we're in good shape, right? I mean, I think that's starting to be respectable. And if we now go look, oh, Blue Angels again today. If we now go look at what's in the file, we should see, yeah, the basic categories there as well as face direction. Each one of these should also now have the information about where it came from in it. What's a little weird is I'm not seeing any of that. Oh, yes, I am. There it is. It's the from field. I'm like, where does that go? Hand glove 02, right? 03. And those are correct. First column, third row. So I think that's all good now. Yeah, and I think we're mostly there. The next thing I want to do, we've got that weird, we're not, our R's and our B's are flipped around, so we kind of need to do a swizzle on the R and the B channel when we import from the PNG. So that's a little bit annoying, but we got to do that. And the other thing that we need to do is we need to think about if we want to downsample. This is a bit annoying, and let me just give you the background of what the problem is. And this is a place where we kind of want to just say, look, we'll do something reasonable. We don't want to go overboard on it. So this is okay. So we now have a problem that we have not had to confront before, but we will have to confront it soon. The problem is that the art assets are made at 1024 by 1024 by 4, right? This is the width. This is the height. This is the bits per pixel. It doesn't take a math savant to know that this is 1 megabyte, right? 1024 times 1024. So if you take 1 megabyte and you multiply it by 4, you get 4 megabytes. That means that every sprite in our game is 4 megabytes of data, right, at its source resolution. The resolution of our screen at the moment is 1920 by 1080. That means that every sprite in our game is made at a resolution that would occupy roughly this much of the screen. Okay? Way too big. Does this matter for us in terms of rendering? No. Why doesn't it matter in terms of rendering? It doesn't matter in terms of rendering because it would be very simple for us to turn mip mapping on. We could downsample our sprites at runtime very easily. Graphics cards can do this on transfer almost. They just do a quick series of renderers and generate it. It's very easy to do. And so we could downsample just in time, and then, it would first cut it in half, and then cut it in half again, and now that's probably the right size, right? So, and just to be clear, what I'm talking about there is we don't want to feed it this texture and then render at this size, because the sampling will be lousy. It'll be all crackly and weird, and not properly anti-aliased at all, right? So we need to do filtering down 2 sizes probably. Down to probably a 256 by 256, right? Is probably more in the ballpark of what we want to start with. Somewhere between 128, 128, 256, somewhere in there. So we could do that. The problem we have is the streaming. Streaming in 4 megabytes per sprite isn't going to fly, right? Let's suppose that there are 200 sprites or 300 sprites on the screen that we need to load. Well, 300 sprites times 4 megabytes, right, equals 1.2 gigabytes. Am I doing that math right? 1.2 gigabytes is way beyond the streaming limit in any reasonable amount of time of older series drives, right? Now, if you're an M2, if you're an NVMe, like M2 drive, or an NVMe PCI, like a PCIe drive, no problem. That takes like 1 second, right? This is like a second or less. So no big deal. NVMe, Xpoint, whatever, like any of these advanced drive technologies, SSD drive technologies on the fast buses, 1.2 gigabytes is not, they don't even care, right? It's no big deal. It would only take a second to stream that in and you're off and running, right? So we'd be able to start up, go, and it would just be fine. But for older drives, this is probably going to be too much, right? So if you take a look, I'm just trying to think of like what an example would be in terms of a minimum platform. What is like HDD read speed right now? For example, pop it up on here. So here we go. So we're talking about something like, let's say worst case is like 50 megabytes per second, or even 100 megabytes per second. So at 100 megabytes per second, we're looking at 12 seconds, right, to load in this thing. It's a little scary. It's a little scary. And we know we don't ever need it to be that big. We're not going to draw sprites at that size pretty much ever, right? The only things we'd be drawing at those size are not our sprites. They're like special case stuff like the title screen. You know what I'm saying? So I think fundamentally speaking, we want to perhaps downsample our artwork right off the bat. Like we may want to halve the size of our artwork because let's suppose that instead of this, we did everything at 512 by 512 by 4, right? So we reduce each of these dimensions by 2. Well, then it's 1 megabyte per. And if it's 1 megabyte per, suddenly this looks a lot better, right? This now looks like 300 megs, which is something like, 3 seconds at 100 megabytes a second, or 6 seconds, right? At 50. So this is starting to look a lot better, especially because we're streaming, so we can bring those things in more gradually. It's not as bad. Furthermore, if we reduce it down again, same thing, right? If 256 by 256 by 4, that is even better. That's 256K, right? That's a quarter megabyte, and it further reduces this into a fraction of a second, right? At a reasonable hard drive rate, we're looking at less than a second to stream in 300 of them. These aren't perfect measurements. Hard drives have trouble with seeking. So it's worth noting that this is not really necessarily fair. The seek times can be pretty bad depending on the situations. SSD drives, the situation gets a lot better, 550 megabytes a second and up, right? 550 megabytes a second is for SSDs not on a good bus. They're not on like a PCIe lanes. This is for like SATA, right? So if we assume that it only gets better from there, and that a lot of times people wouldn't be running them on these, then you can see that 2D6 by 2D6 is a really easy sweet spot to be in. We probably won't hit any trouble, I would imagine. 512 by 512 is probably okay. 1024 by 1024 by 4, I just don't think it's feasible. What we would have to do is try to compress that down, run it through like a PNG style compressor or something if we wanted lossless, or DXT texture compression if we wanted lossy, and just reduce the size that way. But we would have to do something, right? We have to do something. Either we compress the textures some way, lossy or lossless, to get it down 4x from what it is, or more. Or we downsample, and downsampling just seems like a good thing to start with, at least a 512 by 512 by 4, because it just doesn't make any sense to store things at 1024 by 1024. Now, why did I have the art done at 1024 by 1024? Sorry, it never hurts to oversample on artwork. Who knows, in 4 years we might want to do the 8K remaster of Handmade Hero. And all the drives are NVMe drives, and they read at 5 gigabytes a second, and we want all our sprites to be 1024 by 1024 by 4 because it just looks crispier and nicer with those beautiful pixels, right? So you never want to have your artists do the sprites at exactly the resolution that you're going to use. You want to have them do the sprites at a resolution higher than that and downsample, unless you need them to be finicky about every individual pixel, right? Like if you're doing pixel art, they've got to know what the resolution is. But if you're doing hand-drawn, like full painted bitmap stuff, you want to up-res because you're going to want higher quality art assets in the future. Almost certainly, if you ever do a remaster, it's pretty free for the artist to just set the bitmap size in Photoshop to be twice as large as they were going to use, or 4 times as large. And with the exception of the fact that Photoshop tends to be way too slow because it's extremely unoptimized, other than that, it tends to be fine. So that's all I wanted to say. So I kind of feel like we should take our art assets here and maybe downsample them because of that loading pressure. And like I said, the only other option would be to use some other kind of compression. I'm just not sure I want to go that route because again, it overcomplicates the path at this point. We can certainly do more with compression later on if we want to. I just don't know that now is the time for that. So I'm kind of thinking that I don't know that I want to. I don't know that I want to dive into compression at this point, right? So taking a look at this, what we need to do if we wanted to make that happen is once we identify one of these cells as having something in it, when we get to this part, right, and we're going when we're going to actually use the image, what we can do is produce a downsampled version right at that time. And there's a lot of different ways that we can downsample. I will probably pick a box filter for now, but there are other ways of sampling, and it really depends on what you're trying to do. There's a lot of different filters. I even have my own filter that I've made that I use for certain purposes. You can play around with this stuff a lot. It's not worth going into in too much detail right now, but I just wanted to bring that up. So let's go ahead and take a look at how that would work. If there's something in the tile, I want basically a downsample and flip. I know I need to reverse the R and B channels on a ping. So what I want to do here is I want to load in the R, G, and B and A. I want to downsample them. And then I want to write them out. And the other thing that I want to do, and I don't really know which way this... It's a little frustrating. I don't necessarily know what the format in ping implies. I'm not quite sure whether I should pre-multiply the alpha again or whether the PNG has the alpha pre-multiplied or not. Fortunately for me, when we step through in the debugger, it should be obvious whether it's pre-multiplied or not. Because if we ever see a color value higher than the alpha value, it ain't pre-multiplied, right? Because if it's pre-multiplied, it should line up directly with the alpha, right? The brightest you can be is the alpha channel. Is that technically always the case? Not necessarily. It may be that they were using some kind of a gamma curve that we didn't understand, and so the gamma curve is putting the RGB above the alpha because it's gamma corrected after the pre-multiply. I mean, I could make up a situation in which that wouldn't be true, but for the most part, we should not be seeing very high color values and very low alpha values. That's a clear telltale sign that they are not pre-multiplied. If we never see a color value higher than an alpha value, that's a pretty good indication that they are pre-multiplied. I think that's the best I can give you at the moment. All right, so let's take a look. We would need when we come in here, we've got a temp arena. What I would like to do is, we've got this pixel buffer here. We already do a copy out into the pixel buffer, right? That's what this thing's doing. And so I guess we could just push a second one of those on. That's our downscale buffer. We could downsample in place if we wanted to, though, and maybe we just should. There's really no harm in it. Yeah, so we could just downsample in place as well. So maybe we'll just do that. So anyway, when we look here and we take a look what's going on, I'm just going to write a downsample in place because why not? So what a downsample in place looks like is once we've copied these things out into this pixel buffer, what I can do is I can just loop over the size of the downsampled pixel buffer, right? So what I would do here is say, okay, my x is 0, my x is less than the half tile dim, plus plus x, loop over the rows. And what you can see here is for every tile, I'm just going to go through and I'm going to make a quarter-sized version of it. So I'm going to go through half of everything I would have gone through in the normal case. Okay? So in the, when I go to actually produce a pixel, what I want to do here is I want to read 4 pixels, right? And I want to filter them together and then write them out. Yeah. So what I want to do is say, okay, let's get my source pixels out of here. I can, if I want to, actually do sort of the row-based version here. And what that would look like is say, okay, let's take probably do it like this as well. And now I think about it too, if we want this thing to be a block, I would actually need it to be compacted. So now that I think about it, I actually do need it to be smaller, right? I need it to be like 1 smaller than... well, no, I can still write it in place though. So never mind. No, I can still write it in place. Doesn't matter. All right. So if I take the pixel buffer that's the destination, this is where the image currently exists. If I take the pixel buffer and then I use the pixel buffer and the pixel buffer plus 1 row, like right 1 entire x stride. So this is basically like the tile dimension. I guess I can actually do it this way. So here's the first row of the tile, here's the second row of the tile, and here's, again, the first row that I'm writing out. I'm writing it out. So what I can do is I can now say, like, you know, read pixel. And I think we've got, I believe we actually have a thing that's like linear, like up convert kind of a thing. Don't actually know where it is. Thought we had, I mean, we've got those linearized, but I don't know if we have actually ones that unpack. There it is. So here, if I want to unpack the value, I can call RGBA unpack, right? And that will get me back a V4. So I can load all my pixels in like so. So let's load in 2 pixels from the first row and 2 pixels from the second row. So this gives me 4 pixels. It gives me 2 from the first row, 2 from the second row. And then I can choose to do with those what I wish. So if we assume these were stored in sRGB, what I can do here is I can actually do sort of an sRGB convert. I can move them to linear and then move them back. So if I want to do the blend in the proper space, I can choose to do that, which seems like a good idea to me. Looking at what happens when I do the unpack, so if I come down here, you can see the unpack leaves them in the 255 space. So let me go to the linearize here. So if I do these 2 operations as my complement, that would allow me to basically do the blending in a somewhat sRGB corrected space. Remember, this is approximate because we just use squares and unsquares. It's not real sRGB. So if I want to do these unpacks here, that would unpack my pixels. I could then go ahead and change my pixels to be linearized just by passing them all through. And so when I do this sRGB to linear 1, the other thing I could do is swap them. I don't know where that function is. So that's just this. We could make that a shared function. Let's just grab that out and put that in shared. Let's put it down with the pack. Oh, and actually, but we wouldn't really need to call it, would we? Because we could also use the inverse unpacking. Interesting. Interesting. So really what we could do here is say, well, all right, when we do RGBA unpack, right, that's going to unpack the R, the bottom channel into R, right? Which is actually what we want. So we don't need to swap them because the unpack will swap them for us, right? Then when we do the packing, we just have to make sure that we pack them back into the correct place. Because right now it's R's in the bottom channel, it's RGBA, right? And then when we pack it back out, we just want to make sure we pack it back out in BGRA pack. So really, this probably will just work. Hopefully, he says, not really knowing. But once we produce the color value, hopefully that works. It might. Who knows? So if we unpack, linearize, blend, which we haven't done yet, and then pack, that should give us a downsampled and color corrected version. And color swapped R and B version of what we want, right? So to do that, we just need a way to blend these. Let's just start with the obvious. The blended color can just be all these things added together, right? So all we're doing here is saying smush them all together, divide by 4, just take the average. It's a simple box filter. It's the most basic filter you can possibly apply. It has really no bad characteristics that are going to create spurious artifacts, but it tends to blur things maybe a little more than you would like, right? That's its property. Because it doesn't look at any wider area of the image to see whether this was like a hard edge or something that it should try to preserve. It just smushes down. Probably will be fine for our purposes. We will see. Here's the downsample, though. Downsampling by 2x. Once we do that, I guess we can do this part first, actually. Once we downsample by 2x, when we come through here, the tile dim stuff is going to be incorrect, right? And so everything that was using tile dim should be like sprite dim. So I'm just going to say sprite dim, sprite dim, sprite dim. So all that stuff is going to be based on the sprite dim. So here I'm just going to say, all right, after we do that, the sprite dimension is the half tile dimension, right? So now it's downsampling. What are you complaining about? That I hide the declaration of dest pixel? Okay. I don't disagree. Does this make you happy? So now if I come through and look at what's going to happen in that code, I'm expecting to reduce the size of these down to 512 by 512. What's more is actually I could run this more than once, right? I could run this in a for I loop. The only downside is it welds in the reversal of the R and B. And so what we could do is move the R and B up here swap, which is a little slower because it's actually, well, actually it's not a little slower. And in fact, maybe that's better, right? If we do, excuse me. If we did here a BGRA unpack, and instead did a swap, did the swap R and B here, right? That might be smarter because now if we want to, we can actually do this as many times as we want, right? And so this could be a for I loop that allows us to downsample in any way that we wish. So what I could do is say, all right, the sprite dim equals the tile dim, and then this right here is just a downsampler. So we just say, all right, sprite dim equals sprite dim over 2. Something like this, right? So we just do however many downsamples we want. If this is 1 downsample, it runs once. If it's 2 downsamples, it runs twice. This just continues to shrink the thing over and over and over again, right? I think that's right. We got it. I'm waving my hands around a little bit. I haven't thought it through entirely, but I believe that would just allow us to kind of sit there in a loop, shrink, shrink, shrink. Just keep shrinking it down. And yeah, unless I'm missing something. So I don't actually know that we want to run it twice, but maybe we want to go down to 256 by 256, and if we do, that would be the way to do it. So let's go ahead and try this. First things first, let's make it simple on ourselves. I'm not going to run the downsampler at all. So I'm just going to say, look, let's just see if we reverse our channels correctly, right? So let's create a blank import file. Let's run it. And let's see if we get the correct color channels for our weird little sprite there. And so now I think those are actually more correct than they were, right? I think those are more proper. We don't know about the pre-multiplied alpha, though. Now that I think about it, that actually still needs to be corrected. So we're going to have to look at that in a second. I'm going to try... now downsample by 2, just to see if we can produce 256 by 256. Let's see. Del local, create local, and run. Not looking good, if we're honest about it. So let's take a look first of all. Did we get anything obvious wrong? Like, is the file even correct and whatnot? Gonna move to the local dump there and take a look at it. All right, so at least it produced the correct thing, right? It's the right size. It's the right. We didn't do anything obviously stupid, right? So that's good. But what we did do is not actually write out the data properly, so still not particularly encouraging. So let's take a look at what we did wrong here. We could step through this and see what's going on. We're assuming that we're in this pixel buffer thing we're going to write out here, right? This dust pixel buffer. And that's what we write out, if I'm not mistaken, right? Meaning when we reserve the asset data, the thing that we actually write to the file is the pixel buffer. And we write asset data size, which is computed by just taking the sprite dim squared times 4, which is what we want, 2 by 2 by 4, right? So in here, when we do our loops, we're setting it up so that we're looking at the front of the pixel buffer when we start and writing there. Oh, that's our problem right there. So that actually, I mean, it's not our only problem. We probably have other problems than that, but that was one of our problems. So what we actually want to do is set it up to the next row and then divide by 2 so that we're still using the correct thing to reset our tile dim. And it gets smaller each time. Excuse me. Then when we come through here, we do our BGRA unpacks, and let's make sure that's going to the right space. So that's going, yeah, that's correctly going to 255, 0 to 255, right? Then we're taking sRGB 255, which is what we've loaded, and we're bringing that to linear, which is what we want. And then the pack function, BGRA pack, so not correct. We want that, right? And off we go. So let's try that. Oh, you know what? And we need to do the other. Yeah, that we're missing our delinearize too. That would be just, yeah. That's, I just forgot to call the upconvert as well. We need to call this. That's the problem. I shouldn't just multiply 2 to 5. I should actually do the, you know, you want the square root and stuff. So, all right. All right, so we also need to look and see whether we actually have pre-multiplied alpha. So that's one thing I want to do before the end of the stream as well. Let's create a local HHA and let's run. But yeah, because I don't know if that's actually working properly. I'm concerned that it might not be. It probably isn't. So I saw, so we've got a little bit, it looks like we've got some stride issues there with the downsampling. So let's just take a look at that. Oh yeah. So the problem here is that source pixel is pointed to the right place. So we're going to kind of have to keep we're going to have to do this when we do the downsample and we set up these two. Once we're done with a pass, we need source pixel 0 and source pixel 1 to move an extra row down, right? Because source pixel 1 will be pointed where source pixel 0 wants to be, but source pixel 1 needs to be one row below that, right? So we actually need, at this point, to do source pixel 0 plus equals prev dim source pixel 1 plus equals prev dim, right? Every row they need to advance again. So that was a mess up there. Let's try that one more time. But we're almost there. And like I said, the pre-multiplied alpha, we got to go look. Maybe I'll put in some checks that just kind of get some values we can actually look at there. So there's our downsample to 256 version. It looks good. Looking at the edges, I want to say, like, look at those edges. Those edges look a lot to me like it's not pre-multiplied. You know what I'm saying to you? So I kind of feel like that may be a pretty good indication that it is not pre-multiplied alpha. I want to know, though, for sure. And so I want to do a little bit of a scour here and just see what the values are that we're actually getting out, so that I can have some idea of what's going on. So what I want to do is I want to keep, I'm just going to use the blue channel because that looked like a fairly blue sprite. I'm just going to use the blue channel and I'm going to find out, okay, for the max blue alpha diff, I'm going to say it's 0. What I want to do here is say, all right, when I come through here and I've got these values, when I first import them, I'm going to say, like, all right, if P00's alpha value is less than or maybe we'll do blue value is greater than P00's alpha value, right? Then max blue alpha diff equals maximum max blue alpha diff and P00B minus P00A. And so all I'm doing there is I'm going to record that maximum value. So whatever the highest difference is between the B and the A, I'm going to record it. And the other thing I want to do is I want to, in fact, you know what? Let me put it like this. Let's just do it like this. And this will let me store the actual pixel that it found that was the highest diff, right? So what I want to do here is I want to set a breakpoint on the import, and I want to see what it gets for that value. So it's going to run through here one time, and before it hits the second time, I'm going to look at what that value is, okay? So let's force that to do a refresh, a re-import, and then I'm going to take a look at it. So let's bring those two values up, max blue alpha diff C and max blue alpha diff, and run it. And let's see what the values were. So, I mean, yeah. That's a white pixel with no alpha. It is obviously not pre-multiplied. Right? So we know that these are non-pre-multiplied alpha. I think we sort of knew that before, because remember when we were doing the PNG compressor and looking at the RG and B channels? They had stuff in them, right? Where there was no sprite. So we know that's not right. So we need to do the pre-multiply at the end, or at the beginning. I guess at the beginning is more correct. So when we come in here, what we want to do is say, look, we've got to pre-multiply this thing. So when we do the downsample, we can do that. The problem is, if we just did it only on the downsample, it's kind of a problem, because if we only did it on the downsample, then if we don't downsample, it's not going to happen. So we kind of want to do it. We kind of want to do it up in this routine, honestly, unfortunately, right? And so I think what we want to say here is, for each one of these pixels, before we write it out, I think we're going to actually have to follow this. And this is going to be slower, right? But I think we're just going to have to do it. So what we want to do is say, all right, we're checking to see if there's any alpha channel. If there is an alpha channel, then we're going to use it for boundary purposes. But what we also want to do at the same time is make sure that we do an unpack and a repack. Like so. So what we want to do here is unpack the value, do the linearization of it so it's in the right space, relinearize pack, right? This should be a completely neutral operation within rounding error, right? Should just work. Shouldn't change anything other than the swap RGB. And what we do is right here, we do a multiplication of the RGB channel by the A channel. So we force the pre-multiply in the right space. We do the pre-multiply, we unlinearize it back and go, right? I think that's the right place to do it because when you unlinearize, you want it to be right. I'm pretty sure. But with gamma is always a huge mind game. What's happening here? Why is this running anything? We must have done something wrong, because this should not be running anything. What's going on there? Why am I not seeing anything? Something weird is happening, but I don't know what it is. Hold on 1 second, because I wanted to finish what I was doing first, but then I want to see what's going on there. There's my local. What did I break? How could I have broken something? By touching that part of the code? I'm not sure what I broke. Anyway, let's zoom in on that. There we go. So now you can see we get those nice clean edges. And that's because, you know, everything's supposed to be using pre-multiplied alpha here. And since this was coming in with non-pre-multiplied alpha, it was totally breaking the renderer, right? It was not going to compute the right math at all in that case. And so that's importing correctly now. That's right. What's happening if I run a second time? Are we broke? I don't know what broke there. I must have done something weird that I shouldn't have done. Maybe I hit a key I was not supposed to hit. I don't know what happened there. Let's go ahead and test the build in an optimized setting. So if I go ahead and run this here, it's nice and zippy still. So that's good. And if I take a look at how fast the import works for those files on an optimized build, again, just wanted to figure out how slow the import would be. So here it is running. So that's really fast, actually. And that was for 3 files. So I feel like that's totally acceptable because most of the time an artist only updates 1 file at a time. You know, because it takes them Photoshop a while to even export it. So that should be a totally acceptable turnaround time. So I think that's everything. We've got the pre-multiplied alpha in there. We're on startup, we're not doing anything when we detect no changes. Looks like we can survive across runs properly. The dumps look right. Also, let me just dir to make sure the size is right. You can see this is now much smaller, right? It was previously 50 megs, it's 3 now. So that all looks good. And I think we're done. I think that's literally everything. So next week we will be clear to import art assets as we like, which is basically going to involve us deciding how to tag everything and how to specify what we want to load, which is going to be a total old thing. But hey, we want to get art assets in the game. We did all the work to do it, so now we actually have to figure out how we want to specify which ones to use. Not a bad problem to have, right? It's like, hey, at some point you got to figure out how you want to tag things. All right, so I think that's it. We'll go ahead and go to the Q&A. At the end of the while loop of the downsample, shouldn't it be source buffer 0 equals source buffer 1 plus prevdim? Yeah, you might be right. Hold on a second. Let me see. Actually, no, I don't think you are. Sorry. I didn't mean to say you were right and then say you're wrong. No, that looks right to me. So source pixel 0 and source pixel 1 are both pointing at rows. They're going to advance all the way across to the end of their row, and now they're at the next row. That would be correct if it wasn't for the fact that we're trying to advance 2 rows at a time, so they've advanced 1. So this just advances them 1 more row. Does that make sense? Martin said, you added comment for handling big endiness for residual value when calculating the hash, but I feel it is important to mention the same comment should apply also for .at dereferencing in the loop. Yeah, you're probably right. Hold on a second. I don't remember where this is. Yeah, so... Yeah, so you're right, because this is going to be, it's going to use these same shifts and constants, which are they're going to be the wrong way round. Let's just say that. Because, yeah, the start at will load it in big endian or little endian. And at that point, these operations will go the wrong way round. Everything is backwards at that point. So that's a good point, Martins. I didn't think of that when I was typing it in. Am I the founder of Molly Rocket? Yes, Molly Rocket is my company. Does Anna draw vector graphics initially, and would you consider rasterizing vector graphics in the asset system or at startup for a game like this? So actually, I can answer that in a little bit more complex way because this is something that actually kind of annoys me. So no, Anna uses Photoshop, actually. So they are not vector graphics initially. So we cannot consider a rasterization path. I would like that because her style is very cartoony and it could be nicely made, sort of resolution dependent. The problem is Photoshop just doesn't record brushstrokes, right? So we have no ability to make a resolution independent version of Anna's art, even though it would be pretty straightforward if Photoshop just recorded brushstrokes, but don't. Not in a way that it exports, anyway, that I can find. And so it's just not really an option. Your artists have to work in a vector graphics program in order to really have that work in the present day and age. I hope that changes in the future, but right now, not so much. What sort of precision would we be losing by doing the downsamples and doing sRGB linear sRGB rather than doing the linear conversion at the start and keeping it in linear and doing the linear sRGB only when writing out each file? So if you mean what if we just stored a float, well, okay, so there's a couple things you can do. First of all, we could just iterate over the whole block and do the thing in floating point right there. The answer is you would only lose 1 bit per downsample, I think. I can't really think of how you would lose more. Because basically, like, whatever you're storing is just going to have to rounded to the 255, but then you're going to immediately be blending it again. So even if you rounded wrong, you'd have to round wrong the same way on 3 of the 4. Because you rounded the wrong way, it would just cancel out in the next blend. So I don't know. I don't know, Neil. I'd have to think about that a little more, but I suspect the difference would be pretty minimal for this kind of filter. For more wider filters that have uneven weighting, then you probably lose a bit every time, would be my guess. A bottom bit of precision. I don't know that you really... You only lose a bottom bit of precision every time on this one, and really... It's probably actually unlikely, but I don't know. I'd have to think about that some more. Off topic, any suggestion or resource about how to implement a network layer from scratch for a massive multiplayer game? Not really. You're talking about like World of Warcraft or something? Neil, I guess that's a fun thing for me to test out. Yeah, filtering is kind of a really weird sort of topic, and there's a lot of... So here's the thing. We don't really know how to analyze filtering very well. Audio filtering is one thing, because your ears kind of do look at frequency domain stuff, and so analyzing them in terms of digital filters and Fourier transforms is not really a bad idea. To a certain extent, because it actually is more closely related to how you hear. Analyzing digital filters is still kind of something that I don't really find super compelling in a lot of the ways they do it. Because it doesn't really feel like it matches that well with how the brain really does its own visual filtering. And so some of the stuff that they do to analyze filters is kind of hand-wavy to me. It's like, here's a mathematical model that we're applying to analyze this filter, but we've never really justified that model as being something you care about, you know? Because filtering fundamentally is about making things that look good. And if you haven't first proven that your mathematical model correlates well with what looks good, then it's kind of dumb to use, you know? You're just using math for math's sake. And so digital image filtering is kind of a nasty topic. And it's nasty because I don't really feel like we've gotten as good of a hold on it as we really should. And so some of the ways that people analyze these filters in terms of frequency, domain stuff, I think is a little misguided. So I would, it's an interesting thing to look into. Be advised that the writing on it out there is a little hand-wavy, in my opinion. Just curious, are there any games that require more accurate or complex digital filters in the image than those of bilinear or other approximations, like any sort of sharp low-pass filter, etc.? Yeah, so basically you can do a lot of different kinds of filters, and they're and you do it real time. You do use different ones. So if you are filtering image stuff, I think a lot of times people still do bilinear because it's fast and it has no objectionable artifacts. So I don't know to what extent people use more complex filters at runtime for image, just straight up image data. But there's a lot of other kinds of data that gets used in games now. Normal maps, light buffers, like buffers that store like lens effects and stuff like this. So depth of field effects and blurring and that sort of stuff. those often don't use bilinear filters. And they don't use bilinear filters because the kinds of things they're trying to preserve in the filter are better preserved with other methods, right? So max filters or min filters, things like this, other simple filters are sometimes used at runtime that are not bilinear, depending on what it is that you're trying to capture, right? Could you explain again the rotation to the left in the bit pattern you used? Well, no, not really. If you're talking about the murmur hash one, because again, I don't know why they picked these. I don't know why they decided to rotate left. You know, when you're bringing these bits in, they want to mix bits so that low bits mix with high bits and stuff, right? So it's typical to see things rotating a lot. And if you look at rotating it by 31, it's like, well, I want to rotate it by like something that moves the bits in like a marching pattern all around my value, right? So 31 makes some sense. 27, they make sense in a sort of vague hand-wavy way. But no, I don't know why they decided to use these bit patterns. They decided those would mix the bits together in a resilient way. How they decided, I don't know. We'd have to go read the paper and hope that it was written in a way that explains to people who aren't familiar with numerical analysis why it's good, right? I was thinking about a shooter, but let's think we want to support multiplayer for Handmade Hero. Well, I mean, you know, the basics is not super complicated. It's like, look, you've got in Handmade Hero, you've already got the renderer separated from the world sim, right? So you can pull the world sim out and you're going to run the world sim on the server side. And then you're going to run the world sim on the client side. And the problem is that you have to now have a way of reconciling those two things. So what's going to happen is the server has to send to the client what it actually updated in the world. And the client's going to have to fix its representation of the world to match that, right? And it's kind of nasty coding, but you can make it relatively clean if you work at it, you know. Off topic a bit, can you give a quick description of the filter you designed? I'm fine with heavy DSP jargon. Actually, no DSP jargon necessary. I will be posting an article about it. I just haven't quite finished it. It's a very special filter that's designed for a very specific thing, and it had a property that no other filter I've seen has. And so I have an article I was going to write about it. I designed it way back in 2011. It's an old filter, but it just has never been published. So I have a blog post. I just have to finish it up, but you'll be able to read about it. There are no rotate left-right SSC AVX intrinsics. Correct. Not that I know of anyway. I guess what I would say is I don't remember if there are AVX 512 rotations. I don't know if rotate snuck back in there. It probably didn't, but I don't know. Looks like it's there. So I think it did come back in 512. I think they added rotate. So there are. If we ever end up being able to program AVX 512, which seems at this point like a distant dream, 512's got it. Those look like rotate intrinsics to me. My girlfriend appreciates how much you hate on Microsoft and Windows. So do I. But she said your keyboard sounds like someone peeing in the next room, and it has ruined my life. I just need a flush now. When client updates using server incoming updates, assume client simulates locally. It can create discontinuities if simulation diverged. Maybe in HMH it cannot diverge that much though. Yeah, but that's how this works, right? So the SimNet architecture, which is fundamentally the same thing that everyone pretty much uses today, right, is you have a client and a server and they both run the simulation. The client simulation is not right because it doesn't know what everyone else has done. It only knows what it did. So it keeps trying to run along, and the server is running the real version that has what everyone did in it. The server is sending packets to the client to force their simulations to converge. So it's constantly sending the updates to the client that's like, hey, you probably got this wrong, change it to this, right? So that's exactly what the packets are designed to do. The server sends the packets to the client that correct its mistakes. That's what it's supposed to do, right? In the full SimNet architecture, a server simulates every client the same way the client would have updated it, and then it does its authenticated version, and it only sends the diffs because now it knows exactly what the client would be thinking. Most servers today don't do that because it's too much work. But that was the original SimNet architecture. Vatefero, I don't know how to pronounce that. You are correct. Like what most games do is they try to smoothly blend as much as they can between the update of where the client thinks something should be and where the server tells it. And you tend to kind of try to blend between those as much as you can. Sometimes it's just hugely wrong and you can't. You just got to snap it over. But, you know, assuming that it's a slight correction, you just try to blend it. Would you need the brushstrokes or would vector graphics from a conversion tool work? Well, I don't tend to like those conversion tools. They seem to produce pretty bad results in my experience that aren't really that useful for multi-res because they don't really capture what the artist was actually doing. They just sort of capture the pixel result. And I don't know how useful that really is, right? All right, I'm gonna shut it on down. Yeah. All right. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you wanted to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can play around with it. We got a bunch of other stuff on the website. You can check it out. You can use our watch page to watch the series. Whenever we're live on Twitch, it'll show up there. You can watch the stream. It also has the schedule posted at all times so you know when the next time we're going to be live is, and it's got an episode guide that's pretty awesome. You can type stuff in there and it'll search for episodes that have that content in it for you. It's great. So check out that page. Also check out the Handmade Hero Fund if you're interested in supporting community projects like Handmade Network or that episode guide that I just talked about. It's a great way to do it. And finally, if you want to see what else we're up to at Molly Rocket, just click on the Handmade Hero head. It's got all our projects here. You can explore them, as well as my blog. People were asking today about that filter. That'll be posted on here on the blog section as soon as I'm done with that. That's it for today. Hope to see you back here next week when we will. I'm out of delays. I can't delay anymore. I'm out of things to do. I've got to start tagging things. We'll figure out how to do it. We'll roll up our sleeves. I'm wearing short sleeves right now, but I'll wear long sleeves next week, and we'll roll them up, and we will figure out how we want to tag these art assets, and then we're done. We're done with this whole loading foray. We can bind loading to a key, or we can watch a directory. I don't know what we want to do to trigger the reload, but it looks like it's all working, so we're in good shape. So we can have a little party. Hope to see you back here for that. Till then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.